Hi, person on the other side of the computer screen. It's time for lesson 38 and your stuff. And today we're going to be dealing with simplifying expressions using the greatest common factor. Now, in a little while, define that, maybe point out some things about that title and how that might help you understand what in the world we are supposed to be doing. But before we get to that, I need to go through a couple of vocabulary items and conceptual things. Today we're going to be looking at some basic like number theory types of concepts. Number theory just deals with the basics behind like the building blocks of numbers and number systems. So just how do you put a number together? What's a number made up of? And today we'll look at in terms of factors or multiplication. Right, there's two kinds of numbers out there if we're talking about whole numbers, integers, that kind of thing. And that one would be a composite number. Composite number, for example, 220. Because composite numbers have been built up by multiplying smaller numbers to make this bigger number. And in fact, a composite number has been built by taking prime numbers and multiplying them together. Okay, so a composite number can always be broken down into all of its smaller pieces, how it got put together. And 220 can be broken down in lots of different ways, but if we break it down into its prime factors, it would be 2 times 2 times 5 times 11. I think that's right. 2 times 2. Seems like there should be another one in there. 4, 20, 20 times 11. Yeah, that works. Okay, so that's how a composite number is put together, and I picked that one because it's something that's called an amicable number. 284 would go with that one as well. The other category are prime numbers, and prime numbers have that property that you can't divide them by anything else except for themselves and 1. And so up on the board over here, I've got the list of all of the prime numbers less than 100. And if you can't see that, you need to look it up. I gave you a list of prime numbers at the beginning of the semester, but for this lesson, you need to write these down or have them in the back of your notebook so that you recognize these numbers as being prime. I go driving all over the place or ride my bike, looking at mailboxes and then saying, is that prime number? Is that prime number? Or road signs. Going to Oregon, there are mile markers. I do a little, is it a composite number or is it a prime number? If it's a prime number, I break it down before I get to the next mile marker. So here they all are. 2, 3, 5, 7, 11. 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97. Don't they just smell prime to you? You can just like feel that there's nothing you could do to pull those apart. Sometimes you might need to check on a number and say, I'm not sure, I don't have all those memorized. And you can have like a dorky app like I have over here, Prime Number Finder. And if you want to check on something, you can just type in the numbers. So maybe the number's like 697. I mean, is it prime? Is it not prime? It kind of sounds prime-ish, but right away it tells me what the factors of that happen to be. 1 times 117, 41, and 697. So it's 17 times 41. Okay. Pick something else. How about like 1, 2, 3, 4, 5, 6, 7? That one's prime. But if I went back one digit, oh, that's got a whole bunch of factors. So we'll talk more about divisibility rules and all that kind of stuff. We probably have already. That's just all jolly good fun. So there's different ways that people go about breaking down a number to test for its primality or its compositeness. And one thing is just a factor tree. The first thing you would do is just think of two numbers that multiply together to make that number, and then you just start breaking those down. So you take a number like 20, and what's the first thing that pops to your head when you're thinking multiplication tables in 20, besides 1, would be probably 4 times 5. First one I think of. And we'll look at that and say 5 is on my prime list. I'm going to circle that. My tree's done here, but 4 can be broken down into 2 times 2, and both of those are prime. So the composite or the prime factorization of 20 is 2 times 2 times 5. So maybe you've done that before. I kind of like the tree method, but there's another one called the ladder method, where you're doing like division, kind of like upside down division. You'd say, well, the first thing is divisible by is definitely divisible by 2. And if I divide 20 by 2, I get 10. And 10 is divisible by 2 as well. And when I do that, I get 5. And 5 is not divisible by anything except 5 and 1. So I'm going to leave that 1 off. It's not a prime number. But 2 times 2 times 5 happens to be. So finding the prime numbers or breaking a composite down is factoring. It's factoring. Factoring is a form of division. Okay, so what could this number be divided by, and then still there be something else? And prime factorization is an important skill to have. Something that you should practice a lot so you can get good at doing it quickly. You pick anything. You pick like 36, and I can think like 3 times 12, and then 12 is 3 times 4, and 4 is 2 times 2. So there's all my prime factors. 2 times 2 times 3 times 3. Maybe you thought 6 times 6, and it would still break down the same way. You'd have 2 and a 3 and a 2 and a 3. There you go. Now, the next step is to take two numbers at once and see if they share any of these like prime properties to them. So let's take 36 and 24 and break it down into all its prime factors. Okay, so 36 was 2, 18, and 2, and 9, and 3, and 3. There's a totally different way of writing it down. 24 is 2 times 12, and 12 is 2 times 6, and 6 is 2 times 3. So when I look at this, and we're going to write them out, we have 2 times 2 times 3 times 3. And this one is 2 times 2 times 2 times 3. We start seeing what they share, what they have in common. The most number of factors that they share or have in common. Well, there's only 2's and 3's. This one has 2 2's. This one has 3 2's. The greatest number of 2's that we could circle that they both share is 2 2's. And this one has 2 3's, and this one has 1 3. So the greatest number of ones that they share would be this. And we could say that both of these numbers could then be, these numbers could be divided out of them, and then there'd be some stuff left. But both of them could be divided by, well, 2 times 2 times 3, right? Both of them could be divided by 12. 24 can be divided by 12. But that's the greatest amount of common factors that they have. 12 is the biggest number that you could divide both of those and still have something left over. So we do that with numbers, but we're also going to do it with algebra. Okay, so let me clear the board, and then we will do that with, throw some letters and some squared and cubes and things like that in it, and explain how we find that greatest common factor. Okay, what we could, the biggest amount of stuff that we can factor out of everything the same way. That's what common means. Okay, so let me clear the board and we'll move on to a little bit of that. Okay, let's take these two right here. I know that this screen is kind of shiny there, but I've got 8a cubed b to the 5th, and I've got 4 a to the 7th b squared. Okay, I just happened to write that exactly in the worst possible place on the board for you to see that. Let's imagine that this is an algebraic expression, like there's a plus sign between the two of them. And we would like to write that as greatest common factor out here, and then the leftovers in here. Right? This is a sort of a simplification. So we need to find everything that both of these terms are divisible by. And we can do that by breaking it down. We got numbers, right? We got 2 times 2 times 2 makes 8. And then we have some letters. And this one has 3 A's and it's got 5 B's. This one, number-wise, is 2 times 2. 1, 2, 3, 4, 5, 6, 7 A's and 2 B's. So they both have numbers, they both have A's, and they both have B's. We need to find the most that we can commonly remove or factor out of both of those terms. So for the numbers, well, 4 only has 2 2's, and we'll take 2 2's out of there. That means that part of the greatest common factor is 4. A's, well, there's only 3 over here, so we can only factor out 3 out of here because it has to be common. That means we can factor out 3 A's. And then B's, this one has 2 B's, and then we'll factor out 2 B's out of there. The cool thing of doing it this way is that then you see what all the leftovers are, and they can go here in the parentheses. Out of this first one, you have a 2 that's left over. There aren't any A's left over, and you have 1, 2, 3 B's left over. Over here, no numbers, but 1, 2, 3, 4 A's. And you can double check your work by just using the distributive property and multiplying the greatest common factor back into it. So factoring is like the opposite of distribution. Factoring is division, distribution is multiplication, and this helps us to simplify a problem with polynomials and whatnot, because we may need to factor something out or cancel something out, and we can make this a simpler problem by getting rid of things that are common to both numbers. Okay, I'll do one more of these with numbers and letters, and then I'll do one with fractions so you can see why this might actually be simplification. We do want to end up with greatest common factor factored out, and then the leftovers in here. There's going to be 1 here, and there's going to be 1 there. So that's my setup, okay? And then we got to break these down into their pieces. And 15 is 3 times 5. And then we have 1, 2, 3, 4, 5, 6 x's. 1, 2, 3, 4, 5, 6, 7 y's. 9 breaks down into 3 times 3. 5 x's and 1 y. So we start by looking at the numbers. This one's got 3 and 5. That one's got 3 and 3. They each have 1, 3. Circle it. Write it down. We have 6 and 5. So we can circle all these, and we can circle all these but 1. Both of them have 5 x's, at least 5 x's. And then this one's got 1 y, and this one's got a y. We can't factor any more y's out of here because that's all there is. So there's our greatest common factor, and our leftovers are 5. There's an x, and 1, 2, 3, 4, 5, 6 y's. Over here, there's a 3 left, and that's it. So there's our final answer, this factored form with the greatest common factor out there and the leftovers in the parentheses. You can do distribution to double check, make sure you did your math right. I think we did pretty good. You might want to hit pause and take note of this thing up here. I don't have time to go over that too much. You can talk about that in class. Here's where these problems come in handy so we can do the math right. We can only cancel things out if we've got it all down into multiplication and division. So I'm going to take the top here, and I realize that there's a 3 in both of these, and then the leftovers being p plus 1. And now we have multiplication and division. Those 3's can get canceled out to simplify this problem down to p plus 1, which is much better than that original expression. Would you agree? Yeah.